Report in the rescue of a climber who became disoriented and fell on Mount Shasta. We told you yesterday how the 50-year-old fell Saturday but wasn't located and rescued until Sunday.
USGS has just issued a red alert for Mount Shasta, warning that the volcano may be on the verge of eruption. The sudden escalation in volcanic threat level comes after weeks of intensifying seismic activity, ground deformation, and gas emissions around the summit area. This is not a casual upgrade. It reflects a compelling accumulation of real-time data that suggests magma is moving closer to the surface. The term red alert carries weight. It means that the risk of eruption is elevated beyond what is normally tolerated, and that nearby communities, emergency agencies, and scientists must proceed as though an eruption could begin at any moment. Before we start, smash the like and subscribe buttons for more updates. At the heart of the alert is a crescendo of seismic tremors clustered beneath and to the flanks of the volcano. Small earthquakes, previously scattered and mild, have grown in frequency, depth variation, and magnitude. Some of those quakes are now registering in ranges that hint at magma movement or fracture of rock under increasing pressure. At the same time, high-precision instruments are recording unusual rates of ground uplift across the volcano's edifice. The slopes and summit region are bulging outward, as if the mountain is swelling from within. Gas monitoring stations have detected surges in sulfur dioxide and other magmatic gases, signals that molten rock is releasing volatile components as it ascends. In recent days, satellite thermal imaging has shown anomalous heating near summit vents, consistent with shallow intrusive activity. Together, these signals cross a threshold. The volcano is no longer behaving passively, it is waking up. Mount Shasta's geologic past underscores how seriously scientists take these signals. It is a stratovolcano with a long history of episodic eruptions distributed over several millennia, with periods of dormancy of thousands of years between active phases. In the past, eruptions have produced lava flows, pyroclastic explosions, dome extrusions, and significant ashfall. Hazards maps developed by volcanologists suggest that a renewed eruption could threaten infrastructure, roads, waterways, and low-lying communities tens of kilometers from the summit. In short, Mount Shasta is not an unfamiliar volcano. Its dormant stages mask a potential for dramatic renewal if the conditions align. This red alert is more than a mere warning. It signals a fundamental change in posture among volcano trackers. Under this elevated status, USGS monitoring teams are shifting into high gear. Field crews are being mobilized, remote sensors are being doubled or tripled in density, and coordination with state and local civil defense agencies has intensified. Air quality sensors, lahar warning devices, cameras, and radar units may be deployed or reconfigured. Communication channels with authorities are on full alert, evacuation planning, road closures, and public warning protocols are being dusted off and tested. The public may begin to hear about closures of trails, restricted access to forest zones, and emergent advisories for nearby towns and national forests. The implications of this red alert are profound both for the immediate region and for wider volcanic preparedness. For residents in the towns and valleys surrounding Mount Shasta, the alert demands a shift in mindset. What has been a distant, static mountain in their view may soon become a source of ash, lava, and volcanic hazards. Schools, hospitals, utilities, and infrastructure systems will need to revisit their contingency plans. Roads that wind through river valleys could become vulnerable pathways for lahars or debris flows. Rivers and irrigation systems might suffer ash clogging. Emergency services must be ready for the possibility of rapid response in the face of evolving eruption onset. From the perspective of aviation, the alert raises red flags for flight paths. An eruption of even modest magnitude could inject ash plumes into the lower atmosphere, disrupting domestic and regional air traffic. Airlines and aviation authorities will be watching closely, ready to reroute or ground flights if plume forecasts begin to threaten airspace corridors. Exchanges of data between the volcanologists and aviation meteorology offices must become instantaneous. Geologists and researchers are seized by the opportunity and the pressure of now. This is a real-time experiment in volcanic dynamics. Each tremor, each gas spike, each micrometer of ground motion becomes part of a live data stream that can help refine models of magma ascent, eruption forecasts, and hazard projection. Scientists will scrutinize chemical ratios in gases, trace element signatures, isotopic ratios, deformation gradients, and thermal anomalies. Every model that predicted 3D magma conduit geometry will be stress tested. A red alert this close to a potential eruption is rare. The scientific community will be intensely focused on capturing every signal, every precursor, and every nuance. Beyond the immediate science and safety concerns, this situation speaks to larger questions of volcanic risk in populated or sensitive terrain. Mount Shasta lies in a region where people live, recreate, manage forests, and drive highways. It is not a remote volcano in a seldom visited zone. It's part of the living landscape of Northern California. The red alert challenges local governments and disaster agencies to test their readiness in the face of real possibility. It presses us to ask, how well equipped are our hazard maps, our communication networks, and our evacuation routes for an eruption that might unfold over days or weeks or even hours? There is also an element of public perception and response risk. If a red alert is issued and nothing dramatic happens in the immediate hours or even days, some may dismiss it as false alarm. That kind of complacency could blunt reactions if eruption signals intensify later. Conversely, a red alert carries potential to provoke anxiety, rumor, or mass movement of people, even before officials formally mandate evacuations. Balancing transparency with caution is a delicate task. The authorities must communicate uncertainty, explain what scientists know and do not yet know, and avoid inciting panic. The community must be prepared to take warnings seriously, yet not overreact at the first sign of tremor. Logistically, maintaining round-the-clock monitoring under red alert demands resources. Technicians, geophysicists, gas chemists, and communication staff must be staffed continuously. Instrument arrays require power, data links, calibration, redundancy, and backup systems. Remote sensors often depend on solar or battery power. In adverse weather, they may falter. Field crews may have to brave snow, cold, or rugged terrain to maintain or repair installations. The cost and logistic challenge are significant. In parallel, agencies must maintain liaison with state, county, and local emergency management, ensuring that every step is coordinated, data is shared, and decisions are synchronized. At the same time, adjacent jurisdictions will be drawn in. National forests, park services, water districts, highway agencies, and environmental regulators must all collaborate. Access roads might be restricted. Forest fire protocols may be adjusted in anticipation of ash hazards. Water quality systems might prepare for sediment influx, and parks and recreation authorities could close trails or camps. Cross-agency communication becomes crucial in the face of shifting hazard maps and evolving predictions. The red alert also invites reflection on how volcanism is monitored in an era of rapid technology. Modern volcano observatories can combine satellite remote sensing, UAVs, drones, high-speed seismic arrays, ground-penetrating radar, INSAR satellite interferometry, and real-time chemical sensors. In the case of Mount Shasta, USGS, in concert with California Volcano Observatory and partner agencies, will be leveraging these tools aggressively. The data fusion environment, merging seismic, geodetic, gas, thermal, remote sensing, becomes operational. Forecasting must integrate all streams to issue probabilistic forecasts, not certainties. The red alert is a hinge point at which predictive volcanology becomes urgent, not academic. Meanwhile, those who live downstream of the mountain's glaciers, ice fields, or high ridges need to pay attention to what could come. Lahars, volcanic mudflows composed of water and debris, are among the most feared hazards associated with stratovolcanoes. If volcanic heat melts snow, ice, or glacier remnants, the resulting meltwater can entrain sediments and rush downslope at high speed. In the red alert phase, engineers will be revisiting lahar pathways, valley cross-sections, sediment traps, and warning systems. Some locations may need emergency sensors along river channels to detect sudden surges of sediment or water. The timing matters deeply. If the eruption onset is gradual, weeks to months, that gives more time for staging evacuations, deploying barrier systems, and preparing shelters. If the onset is rapid, days to hours, then each hour of forewarning is precious. A red alert effectively budgets time. Each new measurement may raise or lower the probability, keep the alert status, or potentially trigger escalation to eruption imminent status. Politically and administratively, the red alert forces difficult decisions. Officials overseeing land use, tourism, utilities, and transportation may be faced with choices about road closures, restrictions on access to wilderness areas, or preemptive evacuations in zones considered high risk. They must weigh economic, safety, and reputational stakes. If declared too hastily, closures can trigger backlash. Too late, and lives may be endangered. In regions reliant on tourism, parks, and recreation, balancing public access and safety becomes tricky. Insurance and liability layers may also awaken. Utilities, property owners, and public infrastructure agencies may re-examine exposure in zones deemed vulnerable. Emergency response systems may be tested, perhaps strained, especially if multiple agencies must coordinate across county or state lines. Communication networks might be taxed with public inquiries, media pressure, and rumor control. At the national level, a red alert at a major stratovolcano demands attention from federal disaster agencies. The USGS serves as technical lead, but FEMA or analogous agencies may need to be on standby for support. Funds may be reallocated for readiness, air quality monitoring, public communication campaigns, and potential evacuation logistics. Scientific interest and funding may shift temporarily to this mountain. Academic volcanologists may be swept into early response teams or invited to assist in real-time modeling efforts. The red alert also engages public awareness in a new way. For many people, volcanoes seem distant or abstract until they awaken. The striking image of Mount Shasta on the verge of eruption is vivid and dramatic, drawing attention, speculation, and perhaps fear. Local news, social media, and national media may amplify every tremor report, gas spike, or image of plume or steaming. Misinformation and sensational claims might proliferate. Thus, the agencies issuing the alert must double down on clear, transparent, and regular communication. What the signals are, what they may mean, what uncertainties remain, and what steps the public should take now, not later. In the coming hours and days, each new parameter will be weighed as though on a scale. Seismic swarms intensifying into stronger events may raise the alert further, or trigger evacuation thresholds. Gas emissions accelerating or changing in chemical composition may indicate magma freshening or venting. Ground deformation that accelerates could presage imminent surface rupture. Models that simulate magma ascent velocity, fracture propagation, stress distribution, and gas exsolution will be constantly refined. The red alert is not static. It will evolve, possibly escalating through successive stages as precursors coalesce toward eruption. One of the great tensions lies in uncertainty. Even with robust monitoring, no one can say with absolute certainty when, where, or how an eruption will begin. Volcanic systems are complex and do not always follow textbook predictions. Interpreting the signals requires judgment, probabilistic reasoning, and making decisions under pressure. The red alert acknowledges that uncertainty can no longer be ignored. It must be managed. The public, too, must be comfortable with hearing this may or may not happen while taking warnings seriously. In a broader sense, this red alert is a reminder of Earth's dynamism. A majestic mountain in repose, serene and timeless, is capable of abrupt transformation. What seems like normal wilderness is, geologically speaking, part of a living system still capable of abrupt shifts. For communities, scientists, and decision makers, the alert is a test of readiness, cooperation, and responsiveness. Though the red alert speaks to danger, it also embodies opportunity. The ability to watch magma in motion, to measure the birth of a potential eruption, offers scientific insight into processes that have long been hidden. For volcanologists, this is a rare front-row seat. For local agencies, it is a test of institutional resilience. For the public, it is a moment to learn, prepare, and take seriously the presence of active volcanoes in one's landscape. At this moment, all eyes are turned to Mount Shasta. The mountain is more than a geological formation. It is a living entity whose internal unrest is manifesting in measurable, mounting signals. The red alert recognizes that those signals have entered a new regime, one in which eruption is no longer merely possible, but increasingly probable. Each new tremor, gas spike, or bulge may be a footfall toward a long dormant fire. The region waits, watches, plans, and hopes that the warning window affords enough time. The mountain's next moves will test our science, our response, and our humility in the face of deep earth forces. The ground beneath Mount Shasta now resonates with a slow, ominous tension, like a giant deep in slumber shifting in its sleep. With the red alert in effect, the volcano behaves not like a silent monolith, but like a pulse, alive with internal strain. Though no eruption has yet broken the surface, every tremor, bulge, and gas release now carries weight in a narrative of escalating possibility. Deep in the crust beneath the volcano, magma is believed to be pressurizing more vigorously than before. It may be collecting in reservoirs or stalling in dikes, pushing against overlying rock. That pressure is what fractures rock and causes tremors to cascade outward. These fractures open pathways, sometimes minute, for magmatic fluids or hot gases. With adequate pressure, these pathways widen, magma ascends, and the surface can begin to crack and shift. The red alert means that scientists believe that strain is no longer comfortably contained beneath the surface. At this stage, one of the imminent concerns is how the volcanic plumbing responds to new stress. Magma is seldom homogeneous. It contains crystals, gas bubbles, and layers of differing temperature and composition. If new magma pulses from depth rise and mingle with resident magma, gas exsolution, the release of gas from the melt, can accelerate. That release of gas builds pressure internally, sometimes more explosively than rock uplift alone would suggest. Geochemists will now focus sharply on gas ratios, carbon dioxide to sulfur dioxide, helium isotopes, trace volatile species, seeking signs that new, deeper magma is intruding. Such a fresh pulse could precondition an eruption. In parallel, the pattern of seismicity is likely to continue evolving. Rather than just the scattered low-magnitude quakes seen earlier, more robust and perhaps more energetic earthquake swarms may emerge. Some of these might cluster at shallower depths, signaling magma transport. Others may show patterns of migrating seismicity, arcs of activity outlining dike intrusions, or ring fault zones around a rising magma chamber. The moment these events shift upward in depth, or cluster under surprising sectors of the mountain, will attract acute attention. Deformation will likely accelerate. Where the swelling has been slow, geodetic instruments may begin to detect sharper uplift gradients, steeper horizontal strain, or radial extension of flanks. Ground tilt meters might pick up the subtle tilting of slopes outward. GPS stations might diverge more quickly. INSAR satellite radar interference maps might begin to show new zones of swelling or movement previously masked. All of these measures will be paired with inverse modeling to infer where magma is intruding, at what depth, and with what volume. The geometry of deformation, whether doming, elongate dikes, or ring fractures, will help forecast the style of eruption that might follow. Thermal imaging and infrared satellites will be scrutinized more intensely. Any emergent hotspots, new fumarolic activity, steaming cracks, or warming snowfields are flags that heat is nearing the surface. The critical moment is when the thermal gradient steepens sharply near vents or fissures that may signal magma is very near or breaking through conduit walls. In the next days, scientists will compare evolving thermal anomalies with ground heat flow models to estimate how close to surface magma might lie. Another critical factor is hydrology. Mount Shasta hosts multiple glaciers and ice or snowfields, including the Mud Creek Glacier, among others. As magma intrudes and heats subsurface ice or groundwater, melting can accelerate. That meltwater may infiltrate fractures, change pore pressures, destabilize slopes, and mobilize sediments. The interplay of molten rock, meltwater, and structural weakness can generate lahars or debris flows even before a classical eruption begins. If fractures open in water-saturated ground zones, hydraulic pressure may contribute to rock failure. Monitoring stream flow, groundwater levels, and slope stability around glacial zones becomes critical. With flow paths established in valleys, downstream catchments may become vulnerable to sudden flows of water and debris. Even absent explosive ejection, slope collapse from hydrothermal weakening or glacial melt can trigger debris avalanches. Because Shasta's slopes are steep and forested, with valleys carved by rivers, these natural channels could act as conduits for flow. The moment that meltwater mobilizes sediment on steep gradient slopes, the risk of high-velocity flows begins. As scientists parse all these signals, they will update probabilistic forecasts. They will assign increasing probabilities to eruption windows, hours, days, or weeks. The red alert could sharpen into an eruption imminent alert if thresholds are crossed. Models will attempt to quantify the likely size of eruption, duration, vent location, explosivity, and plume height. These forecasts will come with caveats and uncertainties. Volcanoes rarely follow tidy scripts. Communicators must help the public and authorities understand that probabilities evolve with each new measurement. For aerospace and meteorological agencies, the red alert now prompts real-time plume modeling. Even if magma does not immediately reach the surface, steam blasting or gas emission events may generate plumes containing ash or aerosols. Forward projections of winds, humidity, and atmospheric stability will feed ash dispersion models, which in turn will alert aviation authorities. In regions downwind, ashfall risk maps could shift dynamically as vent location, plume height, and wind vectors change. Airlines may already be on standby to adjust routes, cancel flights, or issue warnings. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on Mount Shasta's red alert? Will it erupt soon or calm down? We want to hear from you. Thank you for watching and see you next time.